Welcome to lecture number 12, Control Characteristic of HVDC Transmission System. So the first characteristic of HVDC transmission system, it is an ideal characteristic. It is floated between the DC voltage and the DC current. So under normal operating condition, the rectifier works as a constant current, and the inverter operates with a constant extension angle for maintaining the adequate commutation margin. So the basic for this control philosophy, it is explained using this characteristic, VI characteristic. So the voltage VD and the current ID, it is measured at some common point on the DC line, and we have chosen this to be at the rectifier terminal. So the rectifier inverter characteristic are both measured at the rectifiers, and the inverter characteristic thus includes the voltage drop across the line, right? So you can calculate the inverter voltage VD is equal to VD over I cos gamma plus RL minus RCI into ID. Here we consider the voltage drop across the DC line, it is RLID. So this gives the inverter characteristic with gamma maintained at a fixed value. If the commutating resistance of inverter side RCI it is slightly larger than the resistance of the line, that means if the RCI is slightly larger than the RL, the characteristic of inverter is shown as a CD, has a small negative slope. So since an operating condition has to satisfy both the rectifier and the inverter characteristic, it is defined by the intersection of the point, which is denoted by E, this one. The rectifier's characteristic can be shifted horizontally by adjusting the value of the current command or current order or ID. If the measured current it is less than the command, that means if measured current it is denoted by IM, I measure less than the command, that means I order command, it is denoted by I or D. The regulator advances the firing by decreasing the value of alpha, and the inverter characteristic can be raised or lowered by means of a transformer change. When the tape changer is moved, the constant extension angle of an inverter regulates quickly for restoring the value of the gamma, and as a result the direct current changes, which is then quickly restored by the current regulator of the rectifier. So the rectifier tape changer had to bring alpha into the desired range between 10 to 20 degree. So the range of alpha it is between 10 to 20 degree. For ensuring the high power factor and adequate room for control. And to operate the inverter at a constant gamma, the value of firing is controlled by a computer, which take into consideration variation in the instantaneous value of voltage and current. And normally the value of the alpha it is larger than the deionization angle of the. So this is an ideal characteristic of HVDC transmission system. The next is actual characteristic. So the rectifier maintains constant current by changing the alpha, and however the alpha cannot be less than its minimum value. Once when the alpha reaches its minimum value, no further voltage increases is possible, and the rectifier will operate at a constant ignition angle. And therefore, the rectifier characteristic has a two segment. One is a AB, this one, and another one is AF. The segment AF corresponds to the minimum ignition angle and they represent the CIA mode of the rectifier. And the segment AB, it is in a normal constant current mode of the rectifier. So in practice, the constant current characteristic may not be crudely vertical depending on the current regulator. With a proportional controller, it has a high negative slope due to the finite gain of the current regulator. With a regulator gain of K, we can calculate VD of cos alpha is equal to K into I order minus ID, or you can write VD plus RCR ID. And therefore, we can write the VD is equal to KID or KIOD minus K plus RCR ID. And in terms of perturbated value, the value of del VD it is minus of K plus RCR into del ID. Where del ID it is a change in the current DC current, RCR it is a commutating resistance of rectifier, K it is a gain. This is a basic block diagram of a current regulator. So with the proposal plus integrated regulator, the control characteristic is quite vertical, and the complete rectifier characteristic at a normal voltage it is defined by FAB, and if at a reduced voltage, the new characteristic of rectifier is F dash A dash B. This is at a reduced voltage. Remember that. Now the CEA characteristic, that means a constant extinction angle characteristic of inverter. It is a intersect the rectifier characteristic at E when your system is at normal voltage. However, the inverter CEA does not intersect the rectifier at a reduced voltage represented by F dash A dash B. Here, suppose this is your C inverter characteristic, so it is not intersect the rectifier characteristic at reduced voltage, and therefore a big reduction in rectifier voltage would cause the current and power to be reduced to zero after a short time depending on the DC reactor, and the system would be thus shut down. So in order to avoid the shutdown problem, the inverter is also provided with a current controller which is set at a lower than the current setting for the rectifier, and the complete inverter characteristic is given by DGH. This is DGH. Consisting of two segments, one of CEA and the one of a constant current. This one. So the difference between the rectifier current order and the inverter current order, it is called the current margin, which is denoted by IM. So IM is equal to I order rectifier minus I order. It is usually set at 10 to 15% of the rated current, so as to ensure that the two constant characteristics do not cross each other due to error in measurement or other causes. So under normal operating condition, the rectifier controls the direct current and the inverter is controlling the direct voltage. With a reduced rectifier voltage, the operating condition is represented by the intersection point E dash here. This. And the inverter takes the current control and the rectifier establishes the voltage. So in this operating mode, the role of the rectifier and inverter are reversed. and the change from one mode to the another mode, it is referred as a mode shifting. So this is the basic explanation of a actual characteristic of a HVDC transmission system. So now next characteristic, it is combined rectifier and inverter characteristic of HVDC transmission system. So in most HVDC transmission system, each converter is required to function as a rectifier as well as an inverter. So consequently, each converter is provided with a combined characteristic, which is shown like this one. So the characteristic of each converter consists of three segments. The first segment, it is a CIA ignition relay. That's one. The second segment, it is a constant current. And the third segment, it is related to constant extension angle. So the CIA, it is corresponding to the alpha mean, which we already saw in previous characteristic. The power transfer is from converter 1 to the converter 2, and the characteristics are shown by the solid lines. This one solid lines, and this one. So at that time, the power transfer is possible from converter 1 to converter 2. The operating condition in this mode of operation, it is represented by the E1. The power flow is reversed when the characteristics are shown by the dotted line, which is shown this one. This dotted line. So whenever your characteristic is operating in this mode, at that time your power transfer is reversing, or in other way, if power transfer is reversed, at the time the characteristic is working in this mode. So at that time, the intersection of both the characteristic, it is denoted by E2. So this reverse power source reverse, it is achieved by reversing the margin setting, or by making the current order setting of converter 2 exceeds that of a converter 1. And the current ID, it is same in both the characteristic, but the voltage polarity has been changed when the characteristic work in a power reversal mode. So this is the basic characteristic combined ideal and rectified characteristic of HVDC transmission system. Thank you.